Okay.
Okay.
So our next speaker will be James Dalby, and who is a PhD in mathematics from the University of Strathclyde. So Dalby, James, please.
Okay. Thanks for the introduction, and thanks for the opportunity to speak today. So I'm going to be talking about some work I've recently finished on ferronematics and one-dimensional channels. And this work is a collaboration between myself, my supervisor, Professor Apala Majumdar, and the group from the University of Oxford, Professor Patrick Farrell, and his PhD student, Jingmin Xie. And so we've actually recently submitted this work to the SIAM journal on applied mathematics. So to begin with, what are liquid crystals? So they're classic examples of soft matter, often referred to as the four-phase of matter, and so they're materials that are in between conventional solids and liquids. So this means on the macroscopic scale, they look and flow like liquids, but on a microscopic scale, they do maintain some degree of positional ordering. So in the middle here is the liquid crystal phase, and you can see it's not perfectly ordered like the solid on the left. There is some variation in positional order, but it's not completely isotropic like the liquid on the right. And then liquid crystals are interesting because they are anisotropic materials, and so this means they have a directional dependent response to external stimuli such as light and external fields like electric and magnetic fields. And so here you can see the response to light, in particular liquid crystals polarize light, and as a result you see the different colors in this image. And so my work focuses on the simplest liquid crystal phase, which is pneumatic liquid crystals, where the constituent molecules are typically rod or disc-shaped, and so this means they have long-range orientational order with preferred directions of molecular alignment, which we refer to as the director. And so similar to the first image, you can see there's some variation in positional order, but overall the molecules tend to align along this direction here, which we model by the director N. And so now let's look at some applications of liquid crystals. And so in this first image here, you can see an example of a twisted pneumatic device, which has applications in liquid crystal displays, for instance. And so the idea is you have two glass plates within which you sandwich some liquid crystal, and then they have a surface treatment so that the molecules twist between the two plates. And then two polarizers are placed on the top and bottom at 90 degrees to each other. And so in this state, with an electric field turned off, light passes through the first polarizer, it then gets polarized by the liquid crystal, and so it's still transmitted through the other side. However, then if we turn the electric field on, the orientation changes of the molecules so that they're parallel to the direction of the polarizer at the bottom. And so in this state, since they're at 90 degrees to each other, light is no longer transmitted. And so essentially we can turn the light on and off by turning off or on the applied electric field. And so here is what I think is quite an interesting application of liquid crystals. And so this is for variable contact lenses. Now this is something that isn't currently commercially viable, but the idea is you have a contact lens within which you sandwich a thin layer of liquid crystal. You then have this sort of electrical system, and then you have a device which can turn on and off an applied electric field, similar to this twisted pneumatic device. And so that will change the orientation of the liquid crystal molecules, and that controls whether the lens can be used for short or long distance viewing. So with the electric field off, it can be used for long distance, and with it turned on, it can be used for short distance. And then finally, the most well-known and biggest application of liquid crystals is for liquid crystal displays. And so this includes things like TVs, laptop displays, phones, calculators, watches, etc. And so now onto the topic of this talk, and so that's ferronematics. And these are composite pneumatics, which have magnetic properties. So they usually consist of a dilute suspension of magnetic nanoparticles in a pneumatic liquid crystal host. And the idea behind this is that on their own, pneumatic liquid crystals have a weak or limited magnetic response. However, the addition of the MNPs can substantially increase the magnetization. So even in the absence of an external magnetic field, it has non-zero magnetization. And then ferronematics have similar application to as pneumatics. So that includes pneumatic devices and optical devices, but the difference here is that the switching can now be driven with an applied magnetic field rather than an applied electric field. And so on the right here, you can see some platelet-shaped MNPs in a pneumatic host. And on the left, just a schematic representation of the distortion of the director, which is the blue lines, and the distortion of the magnetic field, which is the orange around the MNPs in red. And so now I want to introduce to you the concept of polydomains. And so these are ferronematic samples which have distinct crystal domains separated by domain walls. And so in each domain, the director and magnetization vector are independently orientated. And so the thick black lines here would be the domain wall, and then inside and out we have distinct crystal domains. And then the converse to a polydomain would be a monodomain, in which there are no domain walls, and so the director and magnetization vectors vary continuously across the domain. And so in these images you can see polydomains formed under different orientations of an applied magnetic field. And so, as I said before, in conventional pneumatics, the switching can be done with an applied electric field, whereas in ferronematics we can now use a magnetic field. And so with no applied magnetic field to begin with, we observe this sample. If we then turn the magnetic field on, so it's coming out of the slide, we switch to this polydomain sample. And then if we apply the magnetic field into the slide, we observe, we switch to this polydomain as well. So in terms of the motivation for this work, this comes from experimental studies done by Mattal and others, in which they demonstrated the existence of a stable dilute ferronematic system using platelet-shaped MNPs in a pneumatic liquid crystal host. And they find the stability of the system arises because of the interplay between the pneumatic forces and the magnetic interactions between the particles. And so motivated by this work, we also consider a dilute ferronematic system, and we consider a one-dimensional channel geometry, which has dimensional or physical width d. So then after rescaling, we just have the domain y's between -1 and 1. And so this 1D assumption is reasonable for channel geometries where the length in the x direction is much larger than the height, the width, I should say, in the y direction, because then structural properties will vary in the y direction only. So now let's look at the mathematical model. And so there's two components to the model, the pneumatic part and the magnetic part, and so we require two order parameters. So for the pneumatic part, we turn to the well-established Landau-Dijen theory, which involves a pneumatic order parameter, which is just a symmetric traced as 2×2 matrix Q, which describes the pneumatic state. And so this Q can be expressed in terms of the scalar order parameter S, which just measures the variation in positional order about the director, as well as the director itself, which is a 2D unit vector pointing in that preferred direction of average molecular alignment, so that Q can be expressed as the following tensor. And then because of the symmetry and tracelessness, and using the definition of N, there's actually only two independent components we need to worry about, Q11 and Q12, whose definitions are given here. Whilst for the magnetic part, we need a polar or magnetic order parameter, which is just a 2D vector M. And so then there's four key dimensionless parameters in this problem that we need to worry about. So there's L1, a pneumatic elasticity constant, L2, a magnetic stiffness constant, psi, which is a measure of magnetic order. In particular, large values of psi will coerce the system to minimize the magnetization energy, which you'll see on the next slide. And then finally, there's C, a coupling parameter, which represents the nemato-magnetic coupling. And all of these parameters are positive. So what we want to do in this work is find the stable, physically realistic, and potentially observable profiles. And so to do this, we need to model them as local or global minimizers of an appropriately defined free energy. So in this case, it's the ferronematic free energy, which is the sum of three contributions. So the first integral is a Landau-Dijen energy, the second a magnetization energy, and the third is a coupling energy. And so the gradient terms in these two integrals account for, well, they're essentially their elastic energy densities, which account for spatial inhomogeneities. And then the remaining terms are bulk terms. And so this one enforces a pneumatic state, this one enforces a non-zero magnetization, and this enforces a co-alignment between the director and magnetization vector. And so then these three non-gradient contributions make up what we call the bulk energy density. And so now let's look at the boundary conditions we consider for this problem. So we take planar boundary conditions on the bottom plate and normal or homeotropic boundary conditions on the top plate for the director. So that means it's pointing in the x direction on the bottom plate and the y direction on the top plate. Whilst for the magnetization vector, we take planar conditions on both plates. So it's pointing in the x direction on the bottom plate and the minus x direction on the top plate. And so we want to find the local or global minimizers, and these will be solutions to the corresponding Euler-Lagrange equations of the ferronematic free energy. And so we want to analytically and numerically study this system of equations. So here's an outline of what I'm going to talk to you about today. And I'll just disclose from the start that in this study we've taken L1 and L2 to be equal to each other, which is a reasonable assumption since L1 and L2 play similar roles for the pneumatic and magnetic energies respectively. The mathematical analysis, when they're not equal to each other, can be carried out in the same way anyway, although in practice L1 would be smaller than L2. L1 would be larger than L2, since this is a dilute suspension, and so the pneumatic effects will be dominant over the magnetic effects. And similarly, since the dilute suspension, taking psi equal to 1 is a reasonable choice, although in practice it would be smaller than 1. But since this is a first study for simplicity, these are reasonable choices to illustrate the concepts and what's going on. So we first of all establish existence of solutions, which I'm not going to talk about because it's not particularly interesting, but we need to establish it. There's then homogeneous solutions, which I'll explain on the next slide, and then inhomogeneous solutions, and there's three things I want to talk about, and then they'll be supplemented with numerical results as we go along. So to begin with, what are homogeneous solutions? Well, they are spatially constant solutions which don't satisfy the applied boundary conditions. So they're solutions of those Euler-Lagrange equations without the derivative terms, and so they are critical points of the bulk energy density, which I've stated here. And we can compute the bulk energy minimizers, and they're given by the following expression here. And what's interesting is we note that we get this alignment condition on the magnetization vector angle phi and the director angle theta, that this difference must be some even multiple of pi. And so you might ask, why do we care about homogeneous solutions? And the reason is because in the limit L tends to 0, we would expect solutions to converge almost everywhere to the bulk energy minimizers, since in that limit we will lose the derivative terms in the Euler-Lagrange equations. However, I say almost everywhere, since for C greater than 0, this rho star is greater than 1, and so this expression won't satisfy the boundary conditions. So we expect convergence in the interior, but then there should be boundary layers at the edges to account for the boundary conditions. So now on to the first result, which is the maximum principle, and I've got up the full energy here again, and that's just to make clear the point that here and hereafter I'm talking about inhomogeneous non-constant solutions which satisfy the boundary conditions. And so we can obtain the following L infinity bound on the solutions, which isn't particularly exciting, but it ties into the numerical results which are coming up, and we will verify that this bound holds, so it is worth mentioning quickly. So now I want to talk to you about an important branch of solutions, and these are order reconstruction solutions. And so these have Q12 and M2 equal to 0, and it's clear from looking at the Euler-Lagrange equations that this branch will always be a solution of that system. And so because Q12 and M2 are 0, this only has 2 degrees of freedom as opposed to the full 4 when they're non-zero. And we can also see, just looking at the definition of Q12, that if it's 0 everywhere, the director angle must be constant, and there must be a jump in order to satisfy the distinct boundary conditions. So we expect the angle to be 0 in one part of the domain and pi over 2 in another part. Whilst the magnetization vector, you can see, will always be pointing in either the positive or negative x direction. And so to begin with, we have a convergence result, which says as L tends to infinity, full solutions of the system should tend to the order reconstruction solution minus y0 minus y0. And this ties into the main result of the work, which is a uniqueness result, which says for a fixed C and sufficiently large L, the order reconstruction solution is the unique critical point and therefore minimizer of the ferronematic free energy. And since it's unique, it is there, so therefore also globally stable in this limit of large L. Now you might ask, what's the physical interpretation of this limit and why do we care about order reconstruction solutions? And so I have the definitions of L1 and L2 in terms of the dimensional parameters here. So L is a pneumatic elasticity constant, kappa is a magnetic stiffness constant, and A and alpha are material and temperature dependent constants. And D is once again the dimensional width of the channel. And so you can see as D tends to 0, L will tend to infinity, and so this limit is relevant for geometries on the nanoscale. And why do we care about OR solutions? Well, that's because they are examples of polydomains, which I was talking about previously. And so in this limit of large L at least, we have two distinct crystal domains separated by a domain wall in both N and M, which is located at the point where Q on 1 and M1 are 0. And so in this case, it occurs in the centre of the domain. And then either side, the direct angle is constant, and so it's 0 on the bottom plate, or the bottom domain, and so pointing in the x direction, and pi over 2 in the top part, so it's pointing in the y direction, and M was either positive in the bottom and negative in the top. And then numerically, if we compute the minimizers for a large value of L, in this case L equals to 10, we indeed only observe one unique and therefore stable solution, which is the OR solution, where Q on 1 and M1 both have the profile minus y. So now let's look at the perhaps more physically relevant limit for systems on the micron scale, and let's look at OR solutions to begin with. And so to do this, we need to introduce the order reconstruction energy, and so this is just the full energy I had up previously, with Q12 and M2 substituted to be 0. We then slightly rescale by timesing by 1 over the square root of L, and we introduce a non-negative OR bulk energy density. So that's just the full bulk energy density I had up before, with Q12 and M2 substituted to be 0, and we subtract the bulk energy minimizer in order to ensure it's non-negative. And then we need to be able to talk about the distance between 2 points for this result, and so we introduced the following metric to do that. And then there are 2 points that are of particular interest, and they are P star and P double star, and these are just the OR bulk energy density minimizers. And so using gamma convergence, we're able to obtain the following rigorous result on the convergence of minimizers of the OR energy as L tends to 0. And rather than repeating word for word this result, I think it's better to sort of explain what these terms represent. And so as L tends to 0, we expect minimizers to converge to a map of this form. And since chi is just a characteristic function on an interval, what this is saying is that the solution takes either the value P star or P double star, depending on where you are in the domain. And obviously if it jumps between the 2 points, then we need to have transition layers to account for the jump. And as I said before, for C greater than 0, rho star is greater than 1, and so this won't satisfy the boundary conditions, so we need to have transition layer, boundary layers as well at the edges. And so we can account for this by minimizing the following functional, j, with respect to the intervals ej. And so this first term accounts for the transition layers between the 2 points. The second accounts for the boundary layer at the bottom plate, and the third the boundary layer at the top plate. And then using this result and second variation analysis, we're able to show that actually for in this limit of small l, OR solutions are unstable with respect to the full ferronemagnetic free energy. So now let's look at some numerical results for small l, and to begin with c equal to 1, and see if they agree with our gamma convergence result. And indeed they do. So you can see the Q11 solutions all converge to rho star in the interior, and then we have boundary layers at the edges to satisfy the boundary conditions, whilst the M1 profiles can tend to either the positive or negative square root of 1 plus 2c rho star, and there can even be transition layers as well if they jump between the two values, and then there's boundary layers again to satisfy the boundary conditions. And then the effect of these different profiles is on the location and the multiplicity of the nematic and magnetic domain walls. So once again, as we saw before, they occur at the points where the solutions are 0, and so all the nematic domain walls occur towards the top plate, whilst the magnetic domain walls can move about. So on this first one, it also occurs at the top plate. In the second solution here, it's at the bottom plate. In the third, it occurs in the middle. And then finally, in this solution, we actually have a difference in multiplicity as well. So we see we have 3 magnetic domain walls and only 1 nematic domain wall. And so now let's do the same thing again and look at a slightly larger value of C, with C equal to 5. And we can observe much the same thing in terms of the convergence in the interior. And then we observe this solution here, for which we have a lot more. So we actually have 5 magnetic domain walls in this solution here. And something else you'll notice is that the maximum of the solutions has now increased in the interior, and this is consistent with the maximum principle and the asymptotic analysis we've done of rho star, for which we see that rho star should grow linearly in C for large C, and so this is what we would expect to see. And once again, so these are unstable critical points in this limit with respect to the full ferronemagnetic free energy. So now let's look at the stable solutions in this limit. So in this case, we're not able to obtain a rigorous gamma convergence result. I mean, we could do, but we haven't done it because it requires a much more difficult application. So in the OR case previously, we had just a finite discrete set of points, namely those 2 points P star and P double star. But in this case, we don't have that due to this alignment condition on the director and magnetisation vector angles, which make things more difficult. But we're still able to do some calculations and formulate an argument from which we would still expect to see minimizers to converge to the bulk energy minimizer, where theta and phi should both be solutions of the Laplace equation, subject to one of these two sets of boundary conditions, and they should once again satisfy the alignment condition which I had up with the homogeneous solutions. And so since these solutions have non-zero Q12 and M2, these are no longer polydomains, and so there should be no nematic and magnetic domain walls. And in this case, we should see continuously varying magnetization and director plots. So now let's look at the numerical results in this case and see if what we observe is consistent with what we expect. And again, let's look at C equal to 1 to begin with. And we can indeed see that the modulus of Q tends to rho star in the interior, and the modulus of M converges to the square root of 1 plus 2C rho star in the interior. And the director and magnetization vector plots vary continuously across the domain. And we can also see that the alignment condition holds, and theta and phi are both solutions of Laplace's equation, subject to one of those two sets of boundary conditions. And so these two solutions I've got here are the energy minimizers for this combination of parameters, and so they essentially just differ in the sign of theta and phi and the magnetization vector plots. And once again, now let's look at a larger value of C, and this time take C equal to 5, and we can observe much the same thing as before, but you'll notice here the big difference is that we have these non-trivial local minima appearing in both mod Q and mod M, and then where these minima occur, we also observe jumps in the theta and phi plots. And if this was to be observed experimentally, these solutions would have distinct optical signatures. And in terms of energy, this solution on the right will have lower energy than the solution on the left, since there's fewer non-trivial local minima, so there's fewer jumps in the solution, which each one will have some sort of energetic penalty, and so this one has lower energy. And finally, let's look at a bifurcation diagram which supports the uniqueness result and the second variation analysis we've done. And so for large L here, you can see we have one unique and therefore stable branch corresponding to Q12 being equal to 0, and so that's an OR solution. And I should have said from the start actually, blue is stable and grey is an unstable solution. Then as L decreases, we undergo a transcritical pitchfork bifurcation, and two new stable solution branches emerge with non-zero Q12, and so these are now monodomains, and they just vary in the sign of Q12. Whilst the OR solution branch persists but becomes unstable, as we expect from the second variation analysis. And actually numerically we can see that as we decrease L further, more and more pitchfork bifurcations will actually occur. So finally, to wrap things up, some conclusions. So in this work we've demonstrated for large L, small d, so for geometries on the nanoscale, the order reconstruction solution is the unique and therefore globally stable minimizer of the ferronemagnetic free energy. And this is important because it demonstrates the existence of stable and physically interesting polydomains. And I should say that currently geometries on the nanoscale aren't currently realizable experimentally, but advances in nanotechnology mean this should be possible, and so this is still relevant work. Whilst on the currently more physically realistic limit of small l or large d, so for geometries on the micron scale, we see there are multiple OR solutions, all of which are unstable, whilst the stable solutions are monodomains, and so they have no nematic and magnetic domain walls. And then I think the key takeaway point of this work is the fact that there's a very complex interplay between the geometry, the material properties, temperature, coupling, and the boundary conditions, all of which come together to have an impact on the solution landscape in terms of the type of solution and their stability, as well as the observable defects in the form of the location and multiplicity of nematic and magnetic domain walls. And so with that, there's my references, and thank you for listening.
Thank you, James. So before we move to the Q&A session, let's unmute ourselves and applaud for James' talk, please. Okay, I'll stop recording.